Hello, welcome to Chapter 8, Homework Questions 40 through 46. Question 40. Esteban used a hinged mirror to create an equilateral triangle, as shown in the diagram below. If the area of the shaded region is 11.42 square inches, what is the area of the entire equilateral triangle? Justify your solution. Well, since he was using a hinged mirror, these triangles right here are all going to be congruent triangles. So therefore the areas are all the same. So if we take 11.42 and times it by 6, we get a value of 68.52, and then that would be in inches squared. So that would be the area of the entire equilateral triangle. Question 41. A house purchased for $135,000 has its annual appreciation of 4%. A, what is the multiplier? Well, remember, we start with 100%. That's the $135,000 that you start with. And then the appreciation, it's going to increase by 4%. So you always are going to start with that 100%, add the additional 4% in. Therefore, the multiplier is going to be the decimal of 104%, or 1.04. That's how much it includes the house purchased and then the additional 4%. Part B, write a function of the form f of t equals a times b raised to the t that represents the situation where t is the time in years after the house was purchased. So the a value represents the initial. So f of t would be equal to the initial price, which is $135,000, and then the multiplier we just found out, which was 1.04, and then raised to the t power. Part C, at the current rate, what will be the value of the house in 10 years? Well, now that we have our equation, we can just plug in 10 for our time, and that will give us how much the value of the house will be in 10 years, and that will be $199,832.98, and that is in dollars. So in 10 years, that's what the house will be valued at. And so make sure that you answer the question in Part C, which wants to know the value of the house in 10 years. So I kind of rewrote it to make sure we were answering the question. Question 42. Copy each triangle below on your paper and state if the shape is convex or non-convex. You may want to compare each figure with the examples provided in problem 8-4. So on Part A, we have a non-convex figure, because when you draw a line from that vertex to the other one there, it's not inside the shape. B will be convex. And so once again, no matter where you draw your lines from vertex to vertex, they will always be inside, so that's what makes it convex. C will also be convex as well for the same reason. And then D will be non-convex, because up top here, right there, you're going to have an issue in terms of it not being inside as well. Question 43. Find the area of each figure below. Show all of your work. On Part A, once again, the way that I do it doesn't mean that it's the correct way, the right way. You might find a different way, maybe even a way that's easier. On A, let's see, I think we need to break this up. Let's go with creating a rectangle, which we have as a 4x9, so we know the area of that is 36. And then we created a trapezoid on top here. But with the trapezoid, we need the height. We have the base, which is 9. We have the other base, which is 5, but we'll know what this height is right here. But I think we can find that out because we have the hypotenuse, and then if this is 9, and then this represents 5 units, that would be 4 right there. So we can use Pythagorean Theorem. You might realize that it is a special right triangle as well, but we'll go ahead and use Pythagorean Theorem just to show that. That's A, so 4 squared plus A squared is equal to 4 square root of 2 squared. That's 16 plus A squared is equal to, that would be 4 squared is 16, square root of 2 squared is 2, so that's 32. Subtract 16, take the square root, and we get A is equal to 4. So let me clean this up a little bit. So we have this distance across, this height represents 4. Now I think we have the information that we need to find the area. This one right here will be 36 because 9 times 4 is 36, and then the area of the trapezoid is 1/2 times the height times the sum of the bases, which would be 5 plus 9. So 2 times 14 is 28. So if we take our 28 plus the 36, that will give us 64 units squared. So the area of this one is 64, and we don't have any units, so we got units squared here. Part B. B, we have an isosceles triangle, so we know both side lengths are 12. We have the included angle at 22 degrees. If we're trying to find the area of a triangle, usually we're using 1/2 base times height. So if we cut the triangle into two right triangles, they're a reflection of each other. We could use trig ratios to find the two things that we need. Once again, we need the base and we need the height. We don't have either one. This angle right here would be 11 degrees, so let's use that right triangle to figure out the rest. We can say that sine of 11 degrees is equal to the opposite, we'll just call this x, over the hypotenuse. Multiply both sides by 12, so x is equal to 12 times sine of 11 degrees. And that's approximately, that'll be x, so then x is approximately 2.2897. Let's go ahead and multiply that one by 2. That will give us this full length here, give us the base, and that will be approximately 4.579. So 4.579. Now we need to figure out what the height of the triangle is, so we will use cosine of 11 degrees. Cosine would be adjacent, so we'll just call this y, over the hypotenuse of 12. Multiply both sides by 12. 12 times cosine of 11 degrees is equal to y, and y will be approximately 11.78. So the area is equal to 1/2 times the base, which was approximately 4.579, times the height, 11.78. So I got the area to be approximately 26.97 units squared. And once again, it doesn't have to be the way that you did it, but just one way to be able to find the area of the triangle. Alright, on part C, we have a right triangle. We're given one leg and the hypotenuse. You might recognize it as a special right triangle, but I'm just going to go ahead and use Pythagorean Theorem to find that third side. So we have 16 plus x squared is equal to 64. Subtract 16 from both sides to get 48, and then take the square root of 48, which is approximately 6.928. Now, in terms of the special triangle, what I was talking about was because the leg is half the hypotenuse, then we must be looking at a 30, 60, 90 triangle. This would be your 30 and then your 60, so the long leg would be the square root of 3 times the short leg, or 4 square roots of 3. So could work out that way as well. And then the area is equal to 1/2 times the base times the height. Once again, you can use 4 square root of 3, or 6.928 approximately. And either way, we'll get an approximation for the area to be 13.9 units squared. Question 84, find the number of sides in a regular polygon if each interior angle has the following measures. Well, we know that the interior angle is equal to 180 times n minus 2, or maybe 180 n minus 360, either way is fine. And then if you divide that by the number of sides, that will give you the interior angle. So we could set it up like this and get 60 is equal to 180 n minus 360 divided by n, multiply both sides by n, so we get 60 n is equal to 180 n minus 360. subtract the 60 in to make this 120 in, add the 360 to the other side, and then divide by 120, and we get n is equal to 3. So that would represent 3 sides of the regular polygon. There are other ways to do it. For example, on B, I'll look at it a different way. If the interior angle is 156 degrees, then we know that we can find the exterior angle by taking 180 minus 156, or 24 degrees. And since the exterior angles always add up to 360 degrees, then you can take 360 degrees and divide it by 24 degrees to get 15. So that would be 15 sides total. Once again, either way is perfectly fine. It's just a matter of what you're comfortable with. On C, 90 degrees, so we're finding the sides. If it is a regular polygon, has an interior angle of 90 degrees. This one you might be able to figure out pretty quickly. If it's 90 degrees, then it's going to have to be a square. But if you go through, once again, kind of the algebra here, you have 90 is equal to 180 n minus 360 divided by n, multiply by n, and then this would give us 90 n is equal to 360, divide, you get 4. So, like I said, this one you might not need to show your work on, just understanding that because it is 90 degrees, if you know, they're going to create right angles, and therefore, but either way is fine. And then D is 140. I'm going to use, once again, the exterior angle version of this, so we can find the exterior angle by subtracting 140 degrees from 180 because they are supplementary. That's 40 degrees, and then because all exterior angles of a regular polygon are going to give you 360 degrees, we're going to divide by 360 divided by 40, and then get x equals, or n equals 9. So this would be 9 sides. Question 45. Determine if the figures below, not drawn to scale, are similar. Justify your decision. So you might remember from back in Chapter 3, potentially, that all circles are similar. And really what you're looking at is a dilation, is that if you take this circle and put it on top of this circle and multiply, in this case the radius is 0.5, so if you multiply by 6, all that does is take this circle and enlarge it by that. The same thing happens with the rest of them. So yes, all of these circles are similar, and in general, all circles are similar. Question 46. At right is a scale drawing of the floor plan for Zynga's dollhouse. The actual dimensions of the dollhouse are 5 times the measurements provided in the floor plan at right. Use the measurements provided in the diagram to find the perimeter and area of her floor plan. So this one, we're only finding the perimeter and area of the floor plan, not the actual one. So make sure we're only looking at the floor plan. So let's start with perimeter. We have most of the side lengths as we go around. One that we're missing is this one right here. And another one it appears that we're missing is this one right here. So we're going to have to use the information that we have to find those missing lengths. So for example, we have this side length as 12, and then this one as 9. So then the, kind of that bottom part that we're missing here is going to be 9 minus 12, which is 3. Now that's just that piece. But then I can add on this additional piece to make up the full side, which would be 6 centimeters. Kind of the same thing on the bottom. We are missing that bottom red piece still, but we know this entire length is 20, so let's piece it together. This length is 8, this length is 4, which is 12, so what's left, that would be 8 centimeters. So the perimeter, if we have all the sides, I'm going to start at the top with 20 and work clockwise. So 20 plus 9 plus 8 plus 3 plus 4 plus 6 plus 8 and plus 12. So add up all those numbers to get the perimeter of the floor plan. And so that will add up to 70 centimeters. Now the next part, we want to be able to find the area of the floor plan. So let's break this up into parts. Once again, it could be done really a lot of different ways here. We could create the area of maybe like the whole thing and then just cut out the missing sections. That's a possibility. We could create the area of different parts. So like here's 3 different rectangles that we could do. We could also go across this way. and create 3 rectangles. So once again, lots of different things that you could potentially do to find the area. I'm just going to pick one and kind of go with it here. Let's break it up this way. We have this length, so that would be 12 times 8, and then we have this one right here, and then that one. So we said this one down here was 8. So 8 times 9 is going to give us 72 here. Then we have 12 times 8, and that'll be 96. So the one that we need is the 4 centimeters, and then what was left? Well, if this is 8 from the bottom, and then 8 here, oh wait, looking at the wrong side. So that's 4 we know, and then this is 9. Well, this one over here was what, 6? So then that means this has to have a 6 as well. So 6 times 4 is 24. So let's go ahead and add those up. We got 96 plus 24 plus 72. And that will be 192 centimeters squared. So now on to part B. B wants to know to draw a similar figure on your paper. Label the sides with the actual measurements of Zinga's dollhouse. What is the perimeter and area of the floor of her actual dollhouse? So you could go ahead and redraw the shape here with the actual sizes. Remember, it is 5 times the measurements provided. So I've taken the figure and I've changed all the side lengths to 5 times what they were. Now this one was 6. I forgot this one. So this would be 30. But the perimeter, since the side lengths are just multiplied by 5, then if you multiply each of those by 5 and add them up, then you should be able to take the previous perimeter and just multiply by 5 to get the new perimeter, which would be 350 centimeters. Now, in terms of the area, how is that going to work? Because the side lengths are definitely getting bigger. The areas would be getting much larger as well. So can we just take 5 times 192? Well, start off just by looking at one of them. This one right here was 12 times 8, which was 96. That's what it was in the model. But now you have, instead of 12 times 8, you have 60 times 40, which is 2400. So that's a lot different than just multiplying 5 by 96. And then let's take a look at this one over here. This was 8 times 9, which was 72. But now it's 40 times 45, which is 1800. And then lastly, this one was 4 times, this one in the middle was 4 times 6, which was 24. Now it's 20 times, I lost it, where are we at? Oh yeah, I don't have it labeled, but it was a 6, so 6 times 5 would have been 30. So 30 times 20 would put us at 600 in that spot right there. So if you look at it that way, now we have an area of 2400 plus 600 plus 1800, which is equal to 4800 centimeters squared. Now, how do those numbers match up? You can kind of look at in terms of that, and it looks like it's kind of getting into the next question as well. So let's go on to C before we jump into that. C says find the ratio of the perimeters of the two figures. What do you notice? So the ratio of if we start with the perimeters, the perimeter of the first one was, so that was 350 centimeters to the 70 centimeters, and what we found out was everything got multiplied by 5, and so the zoom factor was 5, and the perimeter also increased by that same ratio of 5. So on that, I said the ratio equals the zoom factor. And then on D, it's going to want us to look at the ratio of the areas. How does the ratio of the areas seem to be related to the zoom factor? Which I started to jump into a little bit early, so let's get back to the area. We have an area of the actual dollhouse at 4,800 centimeters squared to the model, which was 192. And if you take 4,800 divided by 192, you will get 25. And so I just said that the ratio equals the zoom factor squared. So for example, in this one, the zoom factor is 5. If I square it, I get 25. That's how much the area is increasing from the model to the actual dollhouse.